start. The next speaker is Chantal Staquet from Grenoble. So,
thank you very much. So like the other speakers and I think all the audience, I would like to thank the organizers for organizing this meeting, which I think is extremely interesting for both the talks and the discussions outside the talks. I hope you can hear me.
You have to switch on the microphone.
I should, but I think it's switched on.
You could turn it up.
No, I asked the person who is working with us for this technical problem to increase the power. No, Michael, I'm sorry. You should sit just there. You will be very welcome. Welcome to you.
I'll sit up there.
Okay. So because like Lynn, I shall start up, and after that it will decay toward dissipative effects. So you may not hear me. So I'm going to discuss about the propagation, a joint actually numerical and laboratory study concerning the propagation and dissipation of the internal tide. So I say it's a joint work. The laboratory experiments have been done on the Coriolis platform in Grenoble and have been designed by Joël Sommeria. And regarding the data, they have been the laboratory data have been analyzed by Mehdi Medizadeh, who was an Iranian PhD student with us. And the numerical simulations have been performed by Ivan Perrault, who was a postdoc with us. So let me just recall the motivations of this work. This motivation have to do with some processes linked with the thermohaline circulation you heard a lot about already in this conference. It does not have to do with the forcing of the thermohaline circulation Michael discussed about, or Craig also. It has to do rather with the mixing processes responsible for the upwelling of the deep cold water masses toward the surface. So in the deep ocean, mixing, so I'm considering mainly like Lynn did, processes responsible for mixing far from the boundaries and rather inside the water masses. So in the deep ocean, it has been conjectured, suggested, but this conjecture, as I read papers, become firmer and firmer, that mixing is mostly contributed by internal gravity waves. So the two main sources of internal gravity waves in the ocean are the wind and the barotropic tide, the usual tide, the tide you know. Here is a plot, view graph, a figure from a paper taken from Ekberg and Ray, where they estimate the tidal energy, so the barotropic tidal energy dissipation from altimeter data from the Topex Poseidon satellite. And what they found is that this tidal energy is mostly dissipated at mid-ocean ridges and continental slope, as you can see here at different locations. What they found also, so they did this kind of study both using this satellite data along with the shallow water model, which is actually a model for the barotropic tide in order to estimate the velocities, in order to estimate the current. And what they found is that 25 to 30% of the barotropic tidal energy is lost in the deep ocean and is lost at places where precisely the internal tide is generated, that is at mid-ocean ridges and continental slopes, and hence the fact that it is now written in papers, suggested in papers, that this 25 to 30% loss in the deep ocean is actually the source for internal waves, so at this location in the deep ocean. And this internal waves generated by the barotropic tide is called the baroclinic tide or the internal tide. So what we're going to do here is a study of internal tide at a continental slope. That is, we shall not consider internal tide generation by the wind, but rather by the barotropic tide. And we are mainly doing a so-called process-oriented studies. That is, I'm going to consider a few processes responsible for the loss of energy of the internal tide to small-scale processes eventually responsible for mixing. So briefly the outline, I'm first going to discuss the emission and mostly the spatial structure of the internal tide, and as I just said, consider some processes responsible for energy transfer from the internal tide to smaller scale motions, such as subharmonic motion generated through parametric subharmonic instability, or harmonics motion generated by interaction of the internal wave beam, IW is internal wave beam, with the reflected beam. And Nicolas Grisoire, in a nice poster, I should not say that because I'm involved in this work, but so Nicolas Grisoire in a poster presented another process, which is the soliton generation by interaction of the internal wave beam with the thermocline. So just a brief word about previous experimental and numerical work done of the generation of internal tide at a slope. I just concentrate here about numerical experiments performed by a non-hydrostatic, non-linear of course, but non-hydrostatic model. There has been a lot of work, I would say, or several papers done starting, I think, so done on the internal tide generated by a non-linear hydrostatic model. And I remember the work by Peter Holloway, for instance, in the 80s. So I just would like to, because we are interested in mixing processes, concentrate on non-hydrostatic modeling of waves. So I think the work started with Katiwala in 2003, where he both combined theoretical work of the barotropic to baroclinic conversion of energy, along with some numerical simulation over an isolated topography. This was the case also done by Sonia Legg and her student, and also Kevin Lamp in 2004. I think the first real study of processes associated with the internal tide was done by Kevin, so in this paper. As far as I know, the only numerical work with this type of model of internal tide generation at a continental slope were performed by ourselves, so in these two papers. But now there has been, I would say, several numerical, nonlinear, non-hydrostatic models developed, and so these kind of studies are, I would say, are growing. And I just mentioned that the work done by the Santans team, so people at Stanford who have developed their own code, and which are starting to address this type of problem for much complicated, but I would say more realistic situation, such as considering a realistic topography. As for laboratory experiments, there have been several laboratory experiments, but all focusing on fundamental aspects and mostly related with the structure of the wave beam. So I shall say that next, but as you can understand, so the internal tide is generated by the barotropic tide, so it's oscillatory mean flow over topography. So in a frame of reference attached to this barotropic flow, the mountain, I would say, the bathymetry is oscillating horizontally. And hence, at the first approach, a good model for internal tide generation in the ocean may be simply the consideration of a horizontally oscillating cylinder. And this is a work which has been done by a postdoc of Harris Riney at Austin. So there has been also, as I said, laboratory experiment focusing on the structure of the wave beam over an isolated topography. These are all recent, most of all recent work by Tom Pickup at MIT. And very surprisingly, there was, I don't know if it's surprising actually, it surprises me. There has been some very note, I would say, work by Baines and Fang of the first, I would say, to my knowledge, experimental study of internal tide generation at a continental slope, which has been partly reproduced and, of course, improved both in the method of analyzing the data well, anyway, by Gostio and Doxra. This is a physics of fluids paper. So just very briefly, we all spoke a lot about internal gravity waves. For the purpose of my talk, I need to recall the following thing. This is the well-known Mowbray and Rarity laboratory experiments. In most of the talk, though, I'm going to compare my data with those performed on the Coriolis platform. There will be no rotation. Of course, the rotating platform can non-rotate, and I shall compare my data, unfortunately, with this situation. There has been, of course, laboratory experiment performed in the rotating case, but this is for another talk, maybe. So in the non-rotating situation, This is, so as I said, the experiment, classical experiment of Mowbray and Rarity. So you have exactly this. This is a cylinder which is oscillating vertically in a uniformly stratified fluid. This is the cylinder support, so the cylinder is perpendicular to the screen. And because of the anisotropic dispersion relation of the internal gravity waves, the energy and the momentum of the source can only be carried away along fixed direction, which make a given angle with the vertical, which is dictated by the dispersion relation. So omega is the frequency, oscillating frequency of the cylinder, and n is the Brun-Weisler frequency of the medium. So it's also set. So this is, in a sense, this occurs when the diameter of the cylinder is not too large compared to the boundary layer thickness which exists around the object, because it moves in this stably stratified fluid. But in the situation where the size of the oscillating object is much larger than the thickness of the boundary layer around the object, so this is a beautiful laboratory experiment performed by Louis Gostiaux during his PhD thesis, then you see that things are somewhat different, in the sense that each wave beam here, there are 4, is actually made of 2 wave beams, which each are emitted along line tangent to the object where the shear is maximum, and making an angle with the vertical dictated again by the dispersion relation. So the near field structure looks slightly differently than, I would say, the far field structure. So I will need that a little later. So I said that there have been laboratory experiments performed on the Coriolis platform. So this is a picture of the experiments before water is put. Otherwise, you don't see anything. So you see that the experiments have been performed in a channel which is about 10 meters long, so which extend nearly all across the circular tank. So the channel is made of 2 plexiglass walls, which are 4 meters apart. So as for the forcing, so the barotropic tide is excited by a panel, by a paddle, which is not so visible here, so which closes this channel at one end, and at the other end, by contrast, but you see that the water can escape. Actually, so when the experiment is performed, is carried out, there is water which completely fills the whole tank. So the water, of course, goes over this topography, and when the paddle is moving, then the water goes over the topography, escapes through this region, and comes back after that. Joel told me that they put large cylinder here in order to avoid turbulent, of course, flow to occur, and to minimize the velocity perturbation as the flow comes back in the channel. So as you see here, that we have a topography. So this is the plain, so this is the abyss of the ocean. This is the continental slope, and this is the plateau. And the reason for which the slope of the continental slope is so high, 30 degrees instead of 4 degrees, as it is usually in the ocean, it's, as you understand it, it's because in this 11-meter channel, we want to be able to study what's going on the plain, on the continental slope, and on the plateau. If we had a 4 degrees slope, then we would not be able to study this 3 type of domain. So finally, the measurements, last but not least, you would say. So the measurements are made through a particle image velocimetry. So the image where particles are recorded by 2 cameras. So there are numerical simulation associated, of course, with this laboratory experiment. So as I said, no, I did not say it, but I do it now. So we use the MIT GCM code, which is a nonlinear, non-hydrostatic code solving the Boussinesq equation. So the simulations are direct in the sense that there is no subgrid scale model. So like Craig Winters, we are using very simple boundary conditions, the simplest possible. We wanted to avoid boundary layers, which would be end result with the simulation we have. As in the laboratory experiments, we impose a forcing, but here we impose a forcing at this boundary as well as this boundary. And this forcing, so I would say, forcing are in phase. So when the flow enters here, it escapes here, and vice versa. And of course, the amplitude of the forcing is dictated by assuming that the flux is conserved across the domain. So as I said, the numerical simulation is performed as closely as possible to the laboratory experiments, and hence, like in the laboratory experiments, we consider an idealized continental slope, which is 2D, actually, if you remember. I did not say it, but yes, I showed it. In the laboratory experiments, the slope is two-dimensional, and hence this simulation will be performed in a vertical plane, which is actually this plane here. The stratification will be constant. That is, we shall consider a constant value for n, and I think that's all. That's about all. I think one drawback of the simulations, but the simulations are difficult to perform. I mean, the tank is huge. Is that there is no damping of the internal waves. So as the waves are generated, they will reflect on this wall here, where the forcing is applied. So this is a moving wall in the numerical simulation. This is a paddle in the laboratory experiments. And sooner or later, of course, the flow regime will be affected by the reflected waves. And after some time here, this is about 20, I would say 15 forcing periods, you see that so-called wave attractor occur in the flow. So it's important to work not too late in order to be spoiled, I would say, by this reflected wave. But you will see that it's quite possible to obtain very interesting result, I should say. So this is a first result, a preliminary comparison, I would say, between the laboratory and numerical simulation. So what is plotted here? In most of the plot, it will be like this. So as I said, it's a vertical plane. You recognize here the continental slope. So the forcing is here, and the same, of course, in the laboratory experiments, except that in the laboratory experiment, the forcing is much further. This is one visualization, PIV visualization by one camera, and it corresponds to this region here in the numerical simulation, where the whole domain, by contrast, is shown. So this is the amplitude of the horizontal velocity component, which is filtered at the forcing frequency. So by analogy with the ocean, I shall refer sometimes to this frequency by saying that it's the M2 frequency. And because it's a filtered velocity, it has been averaged over some time, which is indicated here. So what do we see? We see here that there is an internal wave beam, which is emitted at this region here. Exactly the same in the laboratory experiments. So from a qualitative point of view, the agreement is very good. But the amplitude also of this velocity field are about the same, 0.6 centimeter per second. Of course, the amplitude are small. This is a laboratory experiment. This is not fair. This is an academic study. This is not the ocean. And we have, so in this situation, the displacement of the paddle in the laboratory experiment, it's very small. It's 6 millimeter only. I forgot to say that. But so you imagine this 4 meter diameter for this 4 meter wide wall, which is 1 meter deep. I forgot to say that too, and moving only by so with a maximum amplitude of 6 millimeter, and this already leads to the internal tide. But I agree, this is in a weakly nonlinear regime. Actually, when the paddle like this is moving by 2 or 3 centimeter, then the internal tide is extremely turbulent, strongly nonlinear. So I shall focus here, except for one situation, to this weakly nonlinear situation. And hence, so I was discussing about the relative amplitude which match. So we see here that there is one wave beam which is created. So it's quite easy to explain that. So this wave beam is created by, so if I consider a frame of reference attached again to the barotropic tide, this is what I say, then the topography is oscillating. But in this situation, so we have a wave beam emitted by an oscillating topography, by an oscillating motion, by an oscillating obstacle in a stably stratified fluid. But in this situation, the topography is not spatially bounded. It's spatially unbounded, implying that the topography extends here and extends there here, and extends there also. And hence, in this situation, we shall only have this wave beam here, which will be generated. This one cannot be generated. This one not too, because it would enter the topography, and only this one will be created. And hence, we do understand what's going on in this situation. what we see actually that what seems to matter is not so much the whole topography, but rather the shape of the topography at the location where the beam is emitted. And moreover, what seems to matter is rather the radius of curvature at the location where the beam is emitted. And hence we use this idea, which was proposed to us by Bruno Voisin, which was suggested to us by Bruno Voisin, so we use this idea of saying that what should matter actually at the emission region is not the whole topography, but rather the local shape of the topography characterized by its radius of curvature, to compare the laboratory experiments and the numerical simulation with a theory of Hurley and Kitty, in which they predict the along beam velocity for an oscillating cylinder whose radius is exactly equal to the radius of curvature at the emission region. So this is done. This is what is done here, and we see that there is a good agreement between the laboratory experiments, numerical, and theoretical prediction by Hurley and Kitty, where the wave beam is actually emitted. We represented the topography here to make the comparison closer, but in this situation, the wave beam is emitted by a cylinder of radius equal to 1.8 meter. So keeping on the structure of the incident beam, what is done here is the comparison of the along beam velocity as a function of the coordinate, across the beam. So what we plot here is this US velocity component as a function of this coordinate, and we do that during one period, both again in the experiment, numerical laboratory numerical simulation, and for the theoretical prediction by Hurley and Kitty. And so we do that during one period. So what is plotted here is V sub s every 10th period, and hence each profile is plotted, and hence 10 profiles are plotted here. So these give rise to the envelope of the beam from which we can infer some width of the beam. And I'm running out of time. So is it possible now to, since we are looking at the structure of the wave beam, is it possible to define some wave vector, some wave number associated with this beam? In another word, is it possible locally at the center of the wave beam to assume that it may be described by a plane wave, which is both monochromatic in space and time? Of course, it's spatially monochromatic, it's temporally monochromatic, because its frequency is the forcing frequency. But is it also spatially monochromatic? So for this purpose, we plotted the phase of the horizontal component again of the wave field in the numerical simulation and laboratory experiment. And so this is the whole phase field, which is plotted between minus pi and plus pi, which explains why, while the phase is continuously increasing across the beam, there is a sudden change of color, simply because, as you understand, when the phase goes over pi, then it is put to a value which is equal to minus pi. So the fact that the phase increases across the beam is clearly seen here, where the phase is now plotted between 0 and 2 pi as a function again of the distance across the beam. And you see that in the beam center, this phase evolves linearly with this coordinate, which I call sigma, implying that if we assume that locally the phase is the one of a plane wave, both in time, we're not surprised about that, but also in space, then simply the slope here, d phi by d sigma, gives access to a wave number. And it's interesting to notice that in this situation, 2 pi divided by k, which is the wavelength, local wavelength of the wave beam, is found to be the same in the numerical experiment and laboratory experiment, and is about 30 centimeter. I just would like to discuss now about the generation of a parametric subharmonic instability. So very quickly, it has been well known that a plane internal gravity wave is unstable to parametric instability as long as its steepness is smaller than 1. So this has been shown by Hasselmann at the end of the 70s from resonant interaction, necessarily when the steepness is much smaller than 1, and from stability analysis of a primary wave for S smaller, so finite, small but finite value of S. So this was work by Mead, Renzin, and so on. So I should not say so on for authors, I'm sorry, and Klostermeier. So my point here is, how does the parametric instability manifest itself I don't dare to say to look at your panel, but I saw it. So how does the parametric manifest itself? So what I plotted here is the growth rate of the parametric instability as a function of the perturbation of the wave number of the parametrically amplified perturbation. And this is without viscous effect. This is the straight line here, and with viscous effect. So you see that without viscous effect, the growth rate saturates to a constant value, and there is no selection of a wave number for the parametrically amplified perturbation. By contrast, of course, when viscous effects are imposed, then these small scales will be removed by the viscosity. There will be shaded motion will be dissipated, and a scale will be selected. So this scale is selected by viscous effect, and in your numerical simulation by the grid size as well. So how does this parametrically amplified perturbation manifest itself? You see that it manifests itself as bands, which are given structure, which is not surprising. This is exactly the scale associated with this wave number here. And we see that it has a given it has a given slope with respect to the vertical, which comes directly from the dispersion relation of internal gravity wave, in the sense that the frequency of this perturbation, parametrically amplified perturbation, should be half the forcing frequency, implying here that the angle θ1 of this band here has this relation, satisfy this relation, and hence can be predicted from this relation. I'm not clear, but no time to explain more, and I'm sure you understood. So is it possible to find a parametric instability in a wave beam? Actually, there is no reason for that, because we show that a wave beam can be associated locally with a plane wave. And hence, since a plane wave is parametrically unstable, there is no reason not to find a PSI developing in a wave beam. And this was found in this paper. So what is plotted here is the velocity field, horizontal velocity field, filtered at the, I would say, at the half the forcing frequency, filtered at half the forcing frequency. So this is in the case without rotation, and in the case with a rotation. And we see clearly that there is indeed structures whose angle is corresponds indeed, whose angle with the vertical corresponds indeed to half the forcing frequency. So this corresponds. So this is indeed the manifestation of parametric subharmonic instability. Perhaps we can explain why in the rotating case the amplitude is so high, while it's not the case in the non-rotating case. Actually, the reason for that is very simple. If you plot the horizontal crop velocity as a function of the Coriolis parameter, you find that this horizontal group velocity is maximum when f is equal to 0, when there is no rotation, and vanishes at the so-called critical latitude, where half the forcing frequency is equal to f. So it implies that when there is no rotation, then the instability will generate perturbation, and this perturbation will escape from the wave beam, which is located here at this group velocity. By contrast, closer to the critical latitude, the perturbation excited by parametric instability will sit there, will remain there, and hence its amplitude will be larger. So yes, I know. So the most important part of my talk comes now. So now I'm joking, but half. So it's to convince you that we found indeed a parametric instability in the laboratory experiments. I think it's the most important thing to notice, because I showed previously that in the simulation with Theo Gerkema and Pascal Roberto, we found already a PSI in a beam. So this is again the horizontal component of the velocity field filtered at half the forcing frequency, and this is without rotation in the laboratory experiment, and with rotation in the laboratory experiments again. And you see that this is consistent with the heuristic argument I gave previously, that the amplitude is larger with rotation than without rotation. Okay, so just it's possible from the maximum growth rate of the parametric instability for the parameters of the numerical and laboratory experiments, which are the same actually, to predict the vertical scale of the layers which should appear from parametric instability. So this is about 8 to 7 centimeter, and when I just plot the predicted vertical scale onto the numerical simulation and the laboratory experiments, they match quite well the thickness which we observed. Okay, so I'm going to conclude. This was just the generation of harmonics, but I have no time to discuss about that, so I'm sorry to be late. Do I have time to say that?
Go ahead.
I can speak very quickly. Okay, so we found a very good agreement between laboratory and numerical experiments. As I said, the main features of the internal charge are the following. We found that the beam structure and amplitude were in very good agreement with the theory of Hurley and Kitty. This is a GFN paper. So I think one important point, and this was noticed by Victor Schrira, is that so when I presented my result in his laboratory, he thought that this result should be focused. So the internal tide is locally a spatially monochromatic wave, and the thickness of the wave beam is actually half the wavelength, and we found that there could be some mechanism responsible for energy transfer towards small scale, PSI being one of them. Okay, thank you very much. Sorry for being late.
Yes.
Prof, a short question. Is the wavelength the way we found earlier, halfway through your talk, when you were looking at the linear phase dependence, is that wavelength equal to the curvature on the surface where the beam is being emitted from?
Which wavelength? No, I don't.
When you showed the phase dependence being linear across the wave beam.
Oui, d'accord. No, okay.
Right.
So your question is what does set the width of the wave beam? This is your question.
Whether the wave number of the wave beam is actually equal to the curvature on the surface.
No, it's not. No, because it's about 30 centimeter, while the radius of curvature is 1.8 meter.
Okay.
That's an open question. What does set the width of the wave beam? And at the moment, I don't know. But there will be a theoretical study performed in our laboratory, in our team, by Bruno Voisin, in order to try to explain this scale selection, I would
Yes.
say.
One more question.
I agree. The thickness of the wave beam is extremely interesting, and I just want to understand what's lambda in this expression here, so I can relate the thickness of the wave beam to this wavelength, which is which.
I don't know if I have time to
Just
go
roughly.
back, but
It's the horizontal wavelength of something.
I agree it's not obvious. So what I say is that, so what I say is that, so this is one velocity field across the wave beam. So this is the velocity field, the along slope velocity plotted across the wave beam. And you see that the thickness of the wave beam may be estimated by this scale here. And what is plotted here is half the wavelength computed from this plot of the phase field. And I say that the width, I went very, I don't think I showed that because I have no time. I'm sorry.
I see.
So
So lambda is not something I can pull out of the external scales of the problem. This is a diagnostic of the width of
Yes,
the wave.
yeah, this is a diagnostic, and we can discuss about that.
Take one more question, Peter.
At smaller scale, when we do similar experiments, you get beautiful mixing layers which come off the slope, and they're not the same as the PSI, obviously. But do you see those? I mean, is that why you ran the amplitude so low? If you turn the amplitude up, because the on the slope mixing layers on the slope mixing instability produces beautiful staircase.
Yeah.
Staircase of mixed layers coming off the topography.
I don't know. I don't think you can see. They should be asked to draw out because there is boundary layer effects. There is a viscous boundary layer in the laboratory experiments, but not in the numerical simulation.
Yes.
So the fact that these layers here are reproduced with slip and no slip boundary condition, is a strong proof. I would say that it's indeed parametric.
Oh yes, I'm sure that's true. But I just say at larger amplitude, you will also have a competitive effect of these mixed layers, which are streaming off the slope.
I understand. I don't think the data have been analyzed. Can you answer?
But yes, there is boundary layer instability at large amplitude, but this does not really go inside the interior. It does not really mix the inside.
Oh yes, it does. I show you.
Yes, but because we have a very big big size, so this local effect is not able to modify in our situation. It is not able to modify the stratification. It has a very local
In the
effect.
interior.
Seems very long to me. Never mind.